Good afternoon. So initially, I planned to give a presentation on virtualized workloads, but I then decided that I'm going to use this session to talk about something else and raise a question, which is the question in the title of these slides. Preempt equal full, which is full kernel preemption. What is it for? And this is an honest question. I don't have any gotcha, any like, I'm trying to understand it. I'm trying to get into this domain. So no tricks, right? Honest question. And the question is, what is it for? What kind of system needs it? And because we also have preempt voluntary. So next slide is who am I? My name is Giovanni Gherdovich. I am a performance engineer at SUSE, predominantly doing power management and scheduler. I am based in Prague, but originally from Italy. So this is essentially the bulk of this talk. It's going to be probably short, 13 slides. So since 2021, 18 months ago, we have a command line parameter to set the preemption flavor of the kernel, preempt equal. So you don't have to set it at compile time. You can just choose it every time you boot the machine, right? And so before, this was a choice made by the distribution vendor. Now anyone is free to try all the different, all the 3 flavors that are available. And I kind of understand non-voluntary. I trust it. It was made by Ingo, very well-respected developer. And full is the older than voluntary. And I'm wondering if, since all of this, the voluntary and full are written many years ago. Full was written in 2002. I wonder if there is, we kind of forgot a bit of why it was introduced. So I'm gonna show you old emails from the mailing list, old articles from LWN, and kind of go through the history and see how this thing came about. Again, the motivation is that this is very old stuff. The preemption flavors are all of them many decades old, but now we have a command line parameter. So this is why this thing is kind of relevant. And what do you think? This is very bold, very large font. That means I am really asking a question. Introduction on the flavors. First, we're talking about kernel preemption. So the kernel can preempt itself. We're not talking about user space preemption. That's a different thing. So what are those 3 flavors? What do they do? And how are they implemented? The first flavor is called none, and it's the kernel is not preemptible. This is how Linux started, 1991. This is how it was. Then voluntary is a little bit preemptible. There are specific places where you can, where the kernel can preempt kernel code. And where are those places? Where there is this function might sleep, which originally was a debugging aid, and then Ingo Molnar said, let's use those debugging aids and put them contra scheduling in it. They marked where which function are allowed to sleep. So those are good candidates for scheduling points. And so Ingo said, you know what? I'm going to put the contra sched in it and into might sleep, and those are now scheduling points. And then we have full preemption, which is you can the kernel can preempt kernel code can be preempted essentially anywhere, unless when tasks are holding locks. So no preemption some preemption, lots of preemption. The full preemption is when the needless get flag is set, and you're not holding a locks, you can be preempted. I want to also to mention this variable, which is kind of famous if you know about preemption, preempt count, and this is a variable that every task has, and it is incremented when you acquire lock and decremented when you release the lock. So if preempt count is 0, then you're not holding any locks, and so safe to preempt. Thank you. Thank you. That's right. Yeah, this is, yeah, okay, I'm gonna note it. Why not? Because thank you, Joel. So now I'm gonna tell you about this command line parameter, which made all of this very old stuff relevant again. And this is this command line parameter is very popular within SUSE, within my company. We needed it, and it came out of an internal chat session, and it ended up being implemented by Frederick Weisbecker, who's there in the audience, and Peter Zelstra, of course, contributed, and Michael Otzko as well. So what's the problem? Why did we want to set the preemption flavor at boot time instead of compile time? Very practical reason, because we were shipping two different binaries. We have an enterprise distribution and a desk distribution, and maintaining, and the only difference between them is this, is one is voluntary preemption, the desktop one, more responsive, interactive stuff, and the enterprise distro has no preemption, and that was the only difference. And this was causing this, when you do this, you need to do QA, testing, etc. You have two binaries, you know, just because of this difference. So maintenance burden. And I am here quoting this snippet of a chat session we had an internal meeting at SUSE, just to set the record straight, right? who is the how did it came about? It's funny to look back at it from 2020. Michael Matz is actually not a kernel developer, a GCC developer, and we were arguing, how do we go about, do we have different flavors of our distro? Do we do like how many flavors, 3, 4, 5? And Michael Matz, GCC developer, said, you know what? I know nothing, but looks to me this could be runtime config option. And then Michael Otzko from the kernel core team said, that's not a bad idea. And then some brainstorming came about. Oh, yeah, it's just a one-liner patch. Then it wasn't. It was more complex than that. But this is how it started. And in the end, I am here showing the hash of it, which again, Fred, Michael Otzko, and Peter Zelstra. This is one commit of a larger work, but this is the one that adds the parameter. So now your users can choose, and they're going to ask, which one should I choose, right? Should I choose none, voluntary, full? By the way, I'm putting this because this snippet of SysFS 5, you can query them on your laptop right now. You can check which preemption you have reading this file. And if you do not, by default, you have none. You have none. So which one should I choose? So the textbook answer is less preemptible, you have high throughput. More preemptible, you have low latency. So, okay, this is sounds about right, but voluntary and full, what's the difference between them? And in order to answer this, I'd like to get you back and over the timeline of those, of how, when those flavors entered the kernel. So no preemption, this is how it started. 1991, kernel had no preemption. And then, to my surprise, the first flavor that was added was not the middle ground. Like, okay, we start with no preemption, which like easy. Then you have some preemption, which like hard but not as hard, and then full preemption, which you would think maybe it's more difficult. But that's not how it came about. Full preemption was the first one that was implemented in 2002 by Robert Love, which I knew from the book. He wrote a book about kernel development. And so that was full preemption. Then I believe that I also put preempt RT, the birth date of preempt RT, which is not related to preemption flavors, but it's kind of in the same, like, an affine product. I found on the web that 2005 could be a date where preempt RT was first, maybe, I don't know, designed based on 2611 by Ingo and Thomas. 2004. Right. Okay, thank you. Thank you for the correction.
Yeah, that's what I was, but you're right. So in 2005, there were the first functional things around. So it took us a little bit from random patches on the mailing list to get something functional.
Yeah, so 2004. And then voluntary preemption, curiously, around like in a few months later, maybe a year later, we had voluntary preemption. Ingo Molnar and, according to what I found, Arjan van de Ven did the voluntary preemption. And full preemption was already there. Apparently, they didn't like it, right? And they design the voluntary preemption. And this is probably the slides that I would like to, maybe the one that surprised me. Okay, this is a bit long. Please indulge me. I'm going to read most of this text. Okay. So this is a link that I found on archive.org, and it's from Ingo website at Red Hat, but now it's a 404, but it's on the archive. And it's the announcement of voluntary. It's an email from 2004, and it goes like this. So this is Ingo telling the people that he wrote voluntary. And he said, okay, as most of you are probably aware, there have been complaints on LKML that 2.6 kernel is not suitable for serious audio work due to high scheduling latencies. Example, Jacket. I took a look at the latency, and indeed 267 is pretty bad. Latencies up to 50 milliseconds can be easily triggered using common workloads on fast machine 2 gigahertz, even when using the fully preemptible kernel. So Ingo said, fully preemptible kernel, I still get 50 millisecond latencies, and I want to do something about this. To solve this problem, Arjan van de Ven and I went over various kernel functions to determine their preemptibility, and we recreated from scratch a patch that is equivalent in performance to the 2.4 low latency patches. I don't know what low latency patches are. I suppose some patch set that did the low latency stuff. And but it's different in design, impact, and approach, and this is where you can find it. Unlike the low latency patches, this patch doesn't add a lot of new scheduling points to the source code. It rather reuses a rich but currently inactive set of scheduling points that already exist in the 263. The might sleep debugging checks. Any code point that does might sleep is in fact ready to sleep, and at that point, so the patch activates these debugging checks to be scheduling points. This reduces complexity and impact quite significantly. As a practical goal, this patch aims to fix all latency sources that generate higher than 1 millisecond latencies. So from this, I take that Ingo wanted to have more like low latency. His goal was low, not like let's have a middle ground between no preemption. He wanted to go all the way farther than full in terms of low latencies. And that was a surprise for me because it's not like I didn't expect that. And then this is Andrew Morton reviewing the patch from LWN. Actually, this, if you I look at the dates, this is July, and the previous message was October. So this is after. So the Andrew Morton is before the announcement. So and what Andrew Morton says, nope, not going to happen. So this is Jonathan Corbet writing, the strongest objection to the voluntary patch, however, would appear that the 2.6 kernel already implements involuntary preemption. So Andrew Morton said, we already have that. We have full. We don't need your stuff. Via the preemptible kernel option. Any place which calls might slip is already, by definition, preemptible. So the voluntary preemption patch adds nothing which the kernel can't already do. Says Andrew Morton. Please let me repeat. Preemption is the way in which, preemption meaning full preemption, is the way in which we wish to provide low latency. At this time, patches which sprinkle conjure all over the place are unwelcome. After 2.7 forks, we can look at it again. And then Jonathan offers interpretation of why people are writing voluntary. So why are some developers pursuing the voluntary preemption patch? At this time, very few distributors are shipping 2.6 kernel with the kernel preemption turned on, mostly out of fear of creating stability problems. The voluntary preemption patch is a way of getting some of the benefits of preemption without turning on a configuration option that distributors find scary. So this is how John took the Ingo intentions. Okay, I know what Ingo is trying to do. He's trying to get preemption for the masses because distributors don't want to enable preemption, and Ingo is going to find a better preemption. But that's not what Ingo said. So this was July. So a few months later, Ingo wrote the announce, which we just read. Probably it's, I don't know what that was. Okay. So this was July. And Andrew Morton said, no conjure. And in October, as we just said, maybe Ingo changed the pitch and said, okay, this is actually for, performance. This is not cosmetics. So I believe this could have been, I don't know, I mean, I'm not in Ingo's head, but I'm trying to speculate. Just wanted to point out that this is October and Andrew Morton is July. Then this was 2004, jump 10 years ahead. And we have something different. Here we have Peter Ambing saying, why do we have voluntary and full? Let's get rid of voluntary. Because Peter, voluntary is the good one. Let's read it. So Peter Ambing entered the conversation, some thread, with a question. Should voluntary preemption be phased out entirely in favor of full kernel preemption? It turns out that there is still one reason to avoid turning on full preemption. As Mike Galbraith put it, preempt munches, I don't know that word, munches throughput. Like it's bad for throughput. So complaints about the cost of full preemption have been scarce over the years, but evidently it does hurt some cases. So Peter Ambing was saying, full preemption, as the word suggests, is full, and voluntary is something that we don't need. Anyway, I believe, so this is it. If I read Ingo's words from 2 slides ago, that's not what it was supposed to be. And anyway, John goes on and says, there would not seem to be any fundamental reason why full preemption should adversely affect throughput. If the rate of preemption were high, there could be some associated cache effects, but preemption should be a relative rate event in a throughput sensitive system. That suggests that something else is going on. And then Linus Torvald said, okay, you know what? Full preemption is bad for throughput because the compiler generates bad code, something like this. Like it says, A clue about something else can be found in Linus' observation that testing of the preemption count, which happens far more often in a fully preemptible kernel, is causing the compiler to generate slower code. Maybe, I don't know, it seems like maybe Linus knows, I don't know, he has a lot of experience with this, but seems like speculation. I don't know, there is no, whatever. Linus says, the thing is, even if that is almost never taken, just the fact that there is a conditional function called very often makes code generation much worse. A function that is a leaf function with no stack frame, with no preemption, often turns into a non-leaf function with stack frames when you enable preemption, just because you had a RCU region which disabled preemption, whatever. This is like justificate. I don't know exactly if this is correct or incorrect, but what strikes me of this is that Peter Rambin said, we have voluntary and full, let's kill voluntary. While voluntary wanted to kill full, as we saw. So I think that, I don't know, this got lost in the years, I believe. I don't know, I haven't found more information about that. I just wanted to, so this is my last slide. No, I saw a hand, but I was mistaken. So this is my last slide, and this is how the kconfig preempt file advertise the preemption flavors, which is probably the most comprehensive kind of explanation we have in the kernel tree. There's no other documentation, really. So what do we tell our users? Preempt none. No force preemption, parentheses, server. This is the traditional Linux preemption model geared towards throughput. Select this option if building a server, scientific computation system, maximize raw processing power, whatever. None. Preempt voluntary. Voluntary kernel preemption, desktop. Option reduce latencies, adding more explicit preemption points. The new preemption points have been selected. Reduce maximum latency, providing faster application reactions, blah, blah, blah. Run more smoothly, even when under load. Select if desktop. Then we have preempt, which is full preemption. Preemptive kernel, low latency desktop. I find this a little funny. Like, this is desktop, and this is a low latency desktop. Like, what is it? You know, this option reduces the latency of the kernel by making all kernel code preemptible. This allows application to run more smoothly. This is the same code. It's copy paste. It's the application to run more smoothly even when under load. More smoothly even when systems under load, at the cost of slightly lower throughput, okay, and slightly runtime overhead. Select this if you're building kernel for desktop or embedded system with latency required in the milliseconds range. I don't know, it's not very specific. Like, it doesn't really explain which one you should choose. So this is what I had. This is my material. What did I do? I Googled for stuff, found a couple of announcements from 20 years back, and I'm not sure if I'm trying to understand. Yes, what do I want here? Why I'm here? I don't have any data. I don't have any experiment. I'm trying to understand what is the consensus, if there is one, and what is the dominant opinion about those two things that I may not be aware of. Thank you. Please.
Yeah, so I just wanted to mention a few things. So one of the things is with preempt voluntary. So the thing is on like, as you mentioned, on embedded system, config preempt is like really important. And like, because there's fewer CPUs and they're usually overloaded. And there's this weirdness in the CFS scheduler where if you drop the hertz value, now your scheduler ticks are further apart. And if you use nice in a certain way, because something that was supposed to probably run for a short amount of time, but because the ticks are further apart, it runs for longer. Because CFS is quote unquote fair, it makes the higher priority tasks run even longer than it would have gotten to run because it was higher priority. So this effect can be really like magnified if you if you didn't have, either if you reduce the scheduler, if you reduce hertz, or if you turned off preemption as well. So it's really terrible if you did that.
I didn't think of that.
And then the other thing I wanted to mention was, yeah, I'm not sure how these options affect RCU, because with config preempt none, RCU is a lot more simpler, because there's no, you can't get preempted inside a reader section. So the RCU unlock paths are, I believe it's just a compiler barrier. But if you build your kernel with config preempt and then you passed it preempt equal to none, I'm not sure what happens, but I'm guessing it's still. Frederick is right here. He might. Does preempt equal to none simplify the RCU or unlock paths? Or?
So no, it doesn't simplify it.
It does, yes, and just to repeat what Fred says, preempt equal none has the preempt RCU flavor, so there is no such simplification used in the command line parameter.
I also believe that it's preempt equal voluntary doesn't have it either, does it? I think only config preempt has the RCU preempt flavor, so even voluntary preemption.
As you have preempt dynamic, you have RSU preempt. In any case, yeah.
Right. No, what I'm saying is, what's that? Right, that's what I said. Voluntary doesn't need it. No, we were saying that preempt has it and none doesn't. I wanted to make a point that voluntary also doesn't have it. Right, it doesn't need it.
But I guess that RCU read unlock code for preempt RCU is mostly dead code when there is no task queued for task preempted. So it still does the check, but I guess it should be cheap. Should be. Should.
Because you never get into sketch switch with within a preempt disabled section by preemption. So the costly part is if the task is preempted and then it's noted that it's preempted, so the scheduler has to take care of RCU has to take care of it, but this never happens, and so this counter is always 0. So, and then you bail out early in unlock.
Checking whether you should enter the slow path or not on the unlock, and yeah.
No, I'm wondering, well, I guess it could affect branch prediction if you're constantly doing it, because it's still doing the check, whether it's always 0 or not. One question I wonder if we wanted to do, I don't know if I'm gonna get yelled at for this, but what happens if we slapped in that if statement, a static branch, like a static branch on likely or something like that, so that if it's disabled, it's just a no op and never checked. So if in the if statement you do static branch, and when you enable it, it's always, it just jumps to it. Or
is it worth it? I mean, is it measurable? Like, is the impact measurable?
I guess we should measure it.
Yeah. I think we tried. I think Mel did some measurements, and we didn't find really something really measurable. But I guess would be nice to check again. I think. Yeah.
One thing I wanted to ask also is I don't think it's full preemption is one of those situations where if you think you need full preemption, what you really need is preempt RT. I don't think that's the case, right? Because no, it's a different thing, right? The full preemption is latency, preempt RT different. It's not latency. It's
It's really all use case and system dependent. So you have a lot of situations where where full preemption is helpful for you in embedded systems, but you don't need full preempt RT because that's too much overhead. So then there's a lot of things which are more snappy and better schedulable on embedded systems. But there's a capacity problem because embedded systems usually just have a couple of CPUs, while your laptop nowadays has six and more. So that starts to be totally system dependent and application scenario dependent. Also, the voluntary thing was primary for very particular application scenarios where people complained about that preempt full is too much overhead. So yes, you can't make everybody happy.
So voluntary was for audio. That was made for, and that was the use case, no?
That was one use case, but the audio people also run preempt RT, so it's very, very. And I don't think we didn't have CFS back then. I think in 2004, CFS came later. So this was all. The old scheduler was totally horrible in that aspect as well. So that's all a sum of little tweaks here, little tweaks there, and that's you really have to measure it out what it does today.
So in production, we run voluntary, and I think it wouldn't work at all with preempt none. Yeah. Yeah,
We're talking about a server situation over there.
Yeah, so in production in the Facebook Meta data centers, so millions of machines, bunches of different workloads, it's all preempt voluntary. We've had a couple of bugs that we had to fix by tossing in a Condry sched, but it's but it's like I wouldn't need to take off my socks to figure out how many we've had. It's like maybe 5, maybe 10, but not very many.
And for us, they're all kind of the same thing where you're like, oh, why is ksoft IRQD not running? Because we didn't put a Condry sched in a loop somewhere. So it's mostly just about a little bit of fairness instead of like latencies for the workloads.
Yeah. There is a request for mine over there.
So Thomas, question for you. As embedded systems start getting more capacity, does that mean that we don't need preempt equal to full anymore?
Thomas is saying there is always a use case for full. So Bob, if I understand correctly.
You have use cases for none as well. So typical workloads for none is CPU bound, long running, because you want to eat the full time slice, no matter what, and not get shoved out by some event, because just the interrupt came in and you don't want to be rescheduled at that point. So it's more about it really. We have so bad ways to express what the properties of the workloads are. That's one of the issues why we have so many debates about scheduling and schedulers, and no, BPF is not going to fix this problem because we're still not expressing stuff in the right way.
Yeah, it's not going to try.
No, it's going to tinker around the problem.
This isn't on the list of things.
No. I just was preempting the obvious, so fix it with BPF. Now, so as we had the discussion yesterday, so we're really bad. We have these nice values which are ill-defined. We have FIFO, which or priority scheduling, which is even more ill-defined. And then we have deadline, which is broken and hard to use. So what's the choice? So, but we need to come up with interfaces which people actually can use and understand, and which are flexible enough to express the workload needs. So what's the in terms of bandwidth, in terms of responsiveness, and things like that, because that's what people can actually understand and express. But do that in some random nice values. Find the right nice values for 10 related threads, and you're going to spend months on random tunings. I mean, I know I talk to people like who optimize server workloads, and they complain all about that.
Yeah, so that part I'll try and fix with BPF. Absolutely. But not preempt none versus voluntary versus full.
No.
Just to,
But the thing is, BPF is not going to fix the underlying problem that we are so bad at in general about expressing this. And I don't want to have random schedulers in BPF who do something else than what the mainstream should do. That's my main concern about the whole BPF frenzy, because it allows you to circumvent the whole thing and implement something different. And then what the hell, it's valid for your use case, but it doesn't help the general public. We should come up with a set of scheduling configuration constants.
The talk has not even happened.
Useful for the general public, but we debate that in the EDF talk.
yeah, that's what I was going to say. We're preempting this talk for a good reason. So
It's an
we shouldn't do
appetizer
that.
for a talk that is coming. Oh yeah, the question in the back by Andrea Righi. Oh, yes, remote attendee Mel Gorman. Okay.
Yeah, so I was wondering, so in Ubuntu, we are still shipping two different flavors. They're called the generic and low latency. Before this change here, low latency used to have config preempt to be fully preemptible, and also config hers 1000 instead of config hers 250 like the default. Now the latest kernel, of course, doesn't have config preempt anymore because it's all dynamic and can be changed at runtime, but it still has config hers 1000. And we tried to remove that and get rid of this option and just ship generic for everybody. But we got a lot of complaints for the audio people saying, oh no, I tried to switch to generic and it adds jitter to my application or something. I was wondering if this is actually true, or what could be like how config hers. I mean, I understand like if we have more interruptions, high priority tasks get more chance to go sooner because we just interrupt the system more. But on the other hand, we're probably adding a lot more overhead. So what's the best solution here?
To recap your description, you have a 1000 Hz system, and you have preempt none or voluntary in your operating system. In your system. Full.
In low latency, we have full preemption.
Ubuntu low latency has full and 1000 Hz, yet you still get complaints about jitter.
If we set config hers to what I was suggesting is to set config hers 250 both for generic and low latency, and now that we have the dynamic way of setting fully preemption or not, we just can get rid of low latency and ship just one kernel, and so that audio people can set preempt full, and everybody else can just go with the default. But apparently, we got complaints from audio people, and is it really? I mean, are these complaints reasonable? Because they were just complaining, but we didn't get any numbers. So I was wondering if anybody has an answer.
There are maybe. I was thinking you can send such a user a benchmark run, cyclic test, something. I don't know. Would that be representative of audio jitter? It would, right? Yeah. In order to get some quantitative. Mel, oh, yeah, Thomas.
No, but cyclic test doesn't give you any information about if it's an audio stack problem. Then a cyclic test doesn't tell you anything. I mean, it gives you something. It gives you random numbers, but it doesn't help you to understand the actual problem. So you want to have really a proper information what the user is doing and what's the side effects he is seeing. Yeah, stuff like that. I mean, you can do it with phrasing, but you can get just a description. What are you experiencing? I mean, recently somebody came up with, I just simply type an audio file into the def whatever thingy, and it gets hiccups. If I change the kernel back to the previous version, it just runs smoothly. So, I mean, that was even easy to reproduce. So it depends how good the user is in actually providing information. But
Yeah,
that's
so-
always hard to debug user machines.
Right, ask about their setup instead of sending them a benchmark. Mel, is it still available for this question?
It wasn't the question. I don't think that preempt full would go away at any point, or at least not at any point soon, because Thomas pointed out, like, it is really a function of the workload. And when it has looked at none versus voluntary versus full versus preempt RT, they were kind of on a nice curve in terms of throughput versus latency. And full does have better responsiveness, but it's also a lot choppier than voluntary, say. There can be over-scheduling events where something trivial becomes runnable and CFS decides that it needs to run immediately because it's preempt full. So there is a noticeable loss in throughput between voluntary and full. There's not that much of a loss in throughput between none and voluntary, but if you have a workload that must respond within a particular time, then full is more appropriate. But in a lot of cases, it's not necessary. And preempt RT obviously was better again. The no hertz full, or not no hertz full, config hertz equals 1000 actually does have noticeable overhead versus 250. There's a lot more activity that simply happens as a system that is useless. The interrupt handling is higher, but also like load balancing events become higher. Things are more likely to context switch to make small amounts of progress and so on and so forth. So that when the audio people are complaining that it might be jittery, they might have been right, but without knowing exactly what they were doing. Like, was it just audio playback, which would be one class of problem, or was it doing audio recording and encoding on the fly, which is a very different class of problem, and without better quantification for them, can't really help them that much. But full does have a purpose. Deleting it would be not a great idea, because if you need it, you really need it. And while preempt RT is there, it sometimes is a jump too far, because while preempt RT has excellent responsiveness things, its raw performance in terms of throughput can be lower just because of the nature of how it works. But the most important thing to remember is all of this changes over time, because like some of the worst scheduling things that I've seen recently, or that recently been in the last couple of years, had nothing to do with preemption. There was one bad bug where if the idle load balancer was active and a task became runnable, it could actually be a long time before the idle load balancer would hand back control and allow a task to run. And stuff like that is completely independent of what preemption level that you're at. Stuff like that is a complete outright bug. And stuff like that would also not be fixable by PPF schedulers. So preemption changes over time. What was true 20 years ago is not true now, and it's not even true as of 2 years ago. So this question is just going to remain live, but deleting preempt full, it might take a year or two before someone complains, but someone will complain.
Thanks, Mel.
Also, maybe one other point is we should probably define what low latency means. It depends on, I guess, also if you're talking about millisecond latencies, microsecond latencies. I think that there is a difference. I mean, low latency is too general. Just say I want low latency. What do you mean? What do you expect from the system? I guess the answer to the question actually can drive the decision on what you actually need to use in your system.
Yeah, thanks. That's right. Define what low latency is. Milliseconds not the same as microseconds, and as Mel said, lots of bugs are not due to preemption, but other events such as right. Please.
Just going to add a comment to the earlier thing about Hertz. Is it time for a dynamic Hertz? You know, is that something that we should be looking at too? Because we could probably set Hertz to 1,000, but then just slow down the tick rate so we're only doing every fourth, you know. And so, but
Dynamic Hertz would actually be a lot harder than dynamic preempt, because in a lot of cases it's a compile time constant.
Yeah.
So like, there's way too many places that are still talking in terms of jiffies and not time, and jiffies is a function of Hertz. So trying to make that dynamic, an awful lot of compiled constants would become runtime variables instead, and then there's the volume, the absolute sheer volume of Hertz specific sites that would all have to be audited individually.
Yeah, you probably would have to convert all the Hertz muck over to milliseconds first, and then you can convert it and have proper time, and that would work. Yeah, but the problem is, if you have Hertz 1000 and you just then slow down the tick and into Hertz 100, and then you increment 10 jiffies in one go, then a lot of code will get confused like hell.
So we tried to reduce. So we see that. Sorry, can I make a point? Yes, I was trying to make the point that like not having ticks can actually be terrible for power because of CPU idle. The same issue we talked about yesterday. So we tried to drop the Hertz from 1,000 to like 250, and we see power is worse because the CPU idle governor keeps the CPU idle state at a shallow state until it can run again. And so I'm not sure if this is very straightforward that way.
I mean, you could fix the governor there, but Stephen, it's different from no Hertz, because we only skip the tick and at once jiffies in bulk if we are really full idle, if the complete system is idle. Then the lost CPU which goes out goes for a long nap, and when the first CPU which comes back at once is time, but everybody has already armed timer, the hardware timer for the next event. So you actually just skip the time where absolutely nothing happens. But now if you have Hertz 1000 and you do loops, these famous while not time after or before or whatever jiffies, and then this stuff will fall apart. It's definitely interesting experiment, but I'm not sure whether this just works. I expect it to produce really hard to debug problems. So you would have to clean up a lot of the jiffies mess first. I mean, which would be a good exercise on its own, because jiffies is so ill-defined. But yeah, I mean, on the other hand, the timer wheel, we need it just for performance reasons, because that's the place to go for especially for those timers which are mostly cancelled before expiry, which is the vast majority of timer wheel timers, except those which are actually scheduled in the first bucket. So the short-lived ones, so for TCP and stuff, but all TCP timeout and stuff mostly canceled before expiry. So we back then, when we reworked the timer wheel from cascading to non-cascading, I got numbers from Facebook and I got numbers from Google, and there was from full operational service, we had 99% of the timers canceled before expiry, but at the same time we had about 1.something million cascading events per second, which was insane because you cascaded in order to cancel it, which doesn't make sense at all. I mean, we have this other nonsense on the NQ path, which Anna Maria is going to talk about tomorrow.
Sorry to interrupt. This is the end of the allotted time for people.
Okay. We were off in chat mode anyway.
Thank you very much. Thank you very much for contributing.